Hello everyone. So in this video lecture, we'll see about the mathematical representation of Gauss law. So in our previous lecture, we have arrived with the statement of Gauss law. So it is postulated by the scientist Gauss, and also he observed the experimentation of Faraday and finally postulated this law. That is, it states that nothing but the electric flux lines present inside any closed path is always proportional to the charge present inside the path, irrespective of its shape. So normally, everywhere, whenever we want to take off this Gauss law application or Gauss law explanations or Gauss law implementations, anywhere we need actually the some Gaussian surface, some closed surface, the closed irregular shape, what we call it as Gaussian surface. So just to derive its mathematical representation. So we all know that it is represented by Gauss law is represented by surface integral of d dot ds, which is equal to q. So we are just going to arrive that equation. So we are just taking an irregular surface. You could see some irregular path here, some irregular path. So irregular surface is taken, and in that say this is going to have some. This is divided into many surface. Of that, I am taking one surface, that is ds, some differential surface ds, and that is going to have some vector, normal vector an. And if this is creating some flux, then you have some proportionality vector d, electric flux density, and it is always going to have some angle between the two vectors. So you all know that the electric flux lines, an is the normal electric flux lines and d is the electric field intensity. So there is always going to be some angle between theta between the two vectors, and the charge is placed here. So because of this charge, actually the charge distribution, flux lines are produced. So the flux lines passing through the surface will always be equal to q. So the differential surface element what we are taking is ds, and we are taking this at some point P. Anywhere you can take it, but here in this case we are taking at this point P. You can also mention this point to be Q, and you can take it at this point also. So since the surface is not regular, right? Here the surface is irregular. So both the magnitude and direction of the electric flux lines will vary from one point to another. For example, here the point may be maximum, and here when you come at this point far away from the Q, the electric flux lines or the electric field lines may be minimum. Actually, that happens, right? Okay, so now when you just consider a small differential surface element ds, you're just considering small differential small surface in an irregular large closed surface. So now in this case, the ds is nothing but this vector can be represented in terms of ds into an. It's we're using its normal vector, where an is nothing but the unit normal vector to the surface at point P. So this is normal, right? So we can represent any vector using its normal vector. So even though the surface is normal, so it can also point to the opposite directions. Only we have to consider the outward normal in the case of electric field lines, because you all know that whenever you have some field lines, the field lines actually spreads out. So if you have some charge q means, so it will produce some field lines. The electric field lines always spreads out, and the magnetic field lines always curl along the lines. So this is a normal concept. So the electric flux density will make an angle theta with the outward normal surface. So the flux passing through it can also be represented by the normal flux density. So flux is nothing but flux per unit area. So here dn is nothing but flux density. So dn is nothing but flux density, which is nothing but flux per unit area. So dn, it is nothing but why we are representing is as dn means it is the component of d vector. Okay, so component of d vector normal, since it is a normal component, we are representing like this. So first step, we got the expression for dn. Dn is nothing but vector d into cos theta, because it is normal vector. So we are just writing vector d cos theta. And so what is d psi? Psi is nothing but this dn into ds. So d cos theta into ds. Now just use the dot product concept, A dot B. Magnitude of A into magnitude of B into cos theta. When we take the dot product of two vectors, we will get like this. So we just apply this here. So magnitude of D dot ds. This is nothing but magnitude of d dot ds. So now what is this left hand side? It's nothing but d side, the flux. So which is nothing but d dot ds. Now, what about the total flux over closed path? It is nothing but the integration of surface integral of d dot ds. So here the path we can take it as closed path. That is the irregular closed path. So we can also represent psi to be integration of d psi because we are having some closed path. So in that we are just finding out the psi for this small portion. So similarly we can find when we integrate over the whole surface we can find the total flux. So that is nothing but surface integral of d dot ds. Now the surface is very very important here. The closed surface, what we consider here, is called as the Gaussian surface because this is actually an imaginary surface. What we are imagining, and we are just imagining that some charge is there. Okay, so there is some shape is there, some closed path is there. Only then we can just find out the flux density. Okay, so this is the actually mathematical representation of Gauss law. You need to remember psi, which is equal to surface integral of d dot ds, which is equal to q. This is we have just derived this when the charge enclosed is a point charge. When the charge enclosed is a line charge, it again differs. So we have to represent with respect to the line charge density rho L. So we all know that Q is line integral of rho L into dl. So we can just apply that and we can find the value for flux. And if we are just going for the surface charge, then psi is nothing but q, which is equal to surface integral of rho s into ds. And if you just go for volume charge, we can also take the volume charge density. Psi is equal to q, which is equal to volume integral of rho v into dv. So we can, if we just, we can also write the Gauss law psi is equal to q, which is equal to surface integral of d dot ds, which is also equal to volume integral of rho v into dv. So all the formulas can be applied. So if there are more than one charge distributions in Gaussian law, then the total charge is nothing but the sum of addition of all the individual charges. What about this? What is special in this Gaussian surface? So the Gaussian surface may be irregular, so it can be sufficiently large. We can take to be large. It should enclose the entire charge. So always the Gaussian surface must be closed surface. So you have to select the Gaussian surface to be closed surface. Okay. So and also we have to just assume that the when you just take a Gaussian surface, so the electric flux lines is constant over the surface. So the D should be normal to the surface. Okay, so these 3 points you must should be very careful when you select this Gaussian surface. And what are the limitations of Gauss law? So this Gauss law can be applied only to symmetric problems. So if symmetric problem means D should be normal to the Gaussian surface everywhere. So it is not applicable for non-Gaussian surface. That means if the surface is not symmetry, then it cannot be applied. And it should be applied to the surfaces which enclose the volume completely. Okay, so we have lot many applications of this Gauss law. So we can we can find the electric flux lines, flux density. Flux density is represented by D, right? And electric field intensity is represented by E. And the relation between D and E is D is equal to epsilon E. That also you know, right? So this is similar to Coulomb's law. In Coulomb's law application also we found the electric flux lines and field lines. The same way you can find it here also. For an infinite long line conductor, we have just seen the derivation for Coulomb's law for an infinite long line conductor. So we got the formula to be E is nothing but rho L divided by 2 pi epsilon rho. Like that, here also you'll get the same formula when you apply Gauss law. Similarly, you can apply this Gauss law to find the electric field intensity due to an infinite sheet of charge. So here also you have to assume a Gaussian surface, and here you'll get the formula to be rho s divided by 2 epsilon naught. So uh, these are the very important points to be noted in a Gauss law, and how can we represent this Gauss law to be mathematically. So the formula to be remembered is psi is equal to flux is equal to surface integral of rho is d dot ds, or we can also write in terms of that is line charge rho l into dl, or volume charge rho v into dv, or surface charge rho s into ds. Thank you. I hope you understood the concept. Thank you.